All right, thanks everybody. Similar to Henry, we have design challenges at the university for power and cooling and really convincing the facilities folks of handling some of these HPC systems. So today what I'm going to do is talk a little bit about the challenges and solutions we came up with at the university in our constrained budgets and tight cycles. Just to give you an overview of TACC, our mission and strategy is really to enable the scientific discovery and enhance society through the application of advanced computing technologies. We do this in two ways. One is through providing resources and services. This is where we actually evaluate, acquire, and operate a bunch of the systems. But we also perform a lot of research and development as well to complement the resources and services. And this allows us to collaborate with a lot of the researchers on the systems and also conduct our own research and development in terms of software. We work a lot with the Luster community, as was discussed yesterday, and try to push the boundaries of high-performance computing. To give you a quick little overview of the history of systems at TACC and the power required to run these things. In 2001, we deployed the very first IBM Power 4 system. It was 1 teraflop peak performance. That used about 300 kilowatts of total power. In 2003, we went on our first foray into clusters, large-scale clusters, and we deployed a 5 teraflop Dell cluster at the time. And again, that was about 300 kilowatts of total power. We were actually operating those two systems simultaneously in the same machine room. I'll discuss here in a few minutes. In 2006, we then replaced both of those systems with a newer Dell cluster, 62 teraflops. It consumed about 500 kilowatts of total power, 16 kilowatts per rack. And again, the reason I'm setting the stage here is because I want to show you the trends in terms of power and cooling. In 2008, we deployed Ranger. This was a Sun system, 2.4 megawatts of total power, 579 teraflops peak performance. And again, we're talking power densities of increasing here to now 30 kilowatts per rack. So of course, our standard underfloor cooling techniques wouldn't work on this one. We did adopt a different cooling solution similar to what Henry described in the in-row cooling. I have some slides on later. And then finally, earlier this year, we deployed Lone Star 4. This is our 4th incarnation of Lone Star. It's 302 teraflops, 800 kilowatts of total compute power, and this one's about 20 kilowatts per rack. And again, we had to make a design decision here. We actually left space in the racks just to keep the power in the rack low enough for our current data center. So to give you an idea of the two data centers, we have a bit of a challenge here in that we had a really old data center built in 1986. It was originally designed to house Cray big iron systems. It's been retrofitted multiple times. This is the same story you probably hear at many old data centers. We've had to retrofit it with both power and cooling infrastructure, and now we've actually maxed out what we can provide in the room. We have about a total of 1 megawatt of total power in the room, but we're out of chill water. We cannot supply any more chill water into the room. In fact, our campus, where we're located on the research campus in Austin, is completely out of chill water. They're actually working on having to build new big chilling towers. It's an 18-inch raised floor and just has standard crack cooling in that room. In 2007, we were lucky enough that we were working with another group and got a new building, which is very unusual on university campuses. But in that time, we were working with the facilities folks, and we kept trying to explain to them, look, they asked us, well, what are your requirements? And we go, well, we want 12,000 square feet and 5 megawatts of power. And they said, no, you're never going to need that much space or power. And they said, oh, what we're going to give you is we're going to give you 6,200 square feet and 1 megawatt of power. Well, sure enough, we were then awarded shortly thereafter the Ranger system, which required 2.4 megawatts of power. So the machine room was then refitted shortly after being commissioned, so it now supports 4 megawatts of total power, but we're still only limited to about 6,400 square feet total in the room. It's a 30-inch raised floor, so a little bit higher raised floor. It does have crack units in there, and we also have APC in-row coolers on Ranger for that system. So I want to talk a little bit about Commons and our Commons data center. This is the old data center as it was about 2.5 years ago. This was the Lone Star 3. This was the system we deployed in 2006. We had a bunch of other support systems in the room, old Cray systems, some IBM Sun systems, some old Powderhorn silos. We had actually just put in this new SL8500 tape library up there, and we're in the midst of migrating all the data over to it. But as you can see, it's pretty cramped. Some retrofitting of crack units that really weren't positioned in spots that were ideal for running the systems. And also, we had these very old PDUs that were installed in 1986 as well. Had been running for about 20 years by the time we replaced them. They did have their capacitors replaced a couple of times, though. So we then took all of that equipment out, was able to clean out that room when we deployed Lone Star 4. And this is the way our data center looks now. What we did is, and we made some design decisions here for the system. If you notice, we have 4 rows. The equipment is much more spread out. And this is because we actually have a higher power density per rack, and we needed to increase the volume of air around in the various rows. You notice we got rid of some of the old crack units and repositioned some of our 40-ton crack units, and we tried to put them at the ends of the hot aisles so that the hot air would immediately go into them. Of course, we have perforated tiles in all the cold aisles. We also positioned the switch racks right in the middle of each row instead of having them all core at the very center of the system. And some of this was because of cabling reasons. And when I show you the picture of the cabling, I'll talk a little bit more about that. But a few important things. If you notice, space is not nearly as big of an issue. In fact, we have a big area here, but we're completely out of power and cooling in the room. We really don't have any other capacity that we can put in there. So right now we're just putting some low power systems in this area, some stuff that's not quite so dense. Now, just to show you a picture of Lone Star 4, this is the system as it is now. We do overhead cabling, so if you notice, there's the rails up here for the InfiniBand cabling, the switch rack here. Because we were able to position a switch rack in each one of the rows, it allowed us not to have to cross cables across into the rows. So we have a very nicely organized cabling system, and we actually did custom make our own cable management arms that are on the sides of these racks here. So these were custom made. It did leave a little gap here, and we're actually addressing that in some of the cooling issues. The system itself is 22,656 cores, about 44 terabytes of memory, and 1.8 petabyte of disk. So one of the things we were able to do with Dell is after we got the system up and running and in production, we worked with them to do some thermal imaging of the system. And this was kind of neat because it allowed us to identify a couple of issues in the room and also a problem with the switch. What I'm showing here is the front row of Lone Star 4 with the thermal imaging, with the scale here so you can see the cooling. A couple of things to point out. You notice there's some bleed over of the air, hot air into the tops of the racks, but this is only about 80-degree temperature air. Again, this was when the system was running in full production. But what really caught our eye was this red spot here at the front of the switch rack. It turned out that some of the fans in the switch rack weren't running right, and there was a firmware bug that Mellanox had to fix. And we actually had hot air coming out of the front of the switch. Again, this is something we never felt, never knew it was there or anything until we actually did the thermal imaging. It was just an interesting side effect that when we were looking at all the equipment and everything. The other thing is you notice there's some bleed through between the gap where the switch rack is. We're actually working on putting in some plexiglass there so that we can block off some of that air leakage around in the corners. You'll also see in another image we have leakage around the ends of the row. But again, we were struggling. We had a very limited budget that we had to work in. We were working in an old data center, and we were trying to do whatever we could to get this system installed in a timely manner. So, a couple of more thermal imaging. So this is the ends of the rows. This is the back of the rack. You can see that the scale is much hotter now. We're up to 42C in these very hot regions in the backs of the racks. But again, here at the end of the row, you see some bleed over where you have nice cool air at the bottom, a couple of chassis in the rack. But you do have some leakage of hot air around the edges. Interestingly enough, you can actually see a person standing right there and a ladder right behind them. That was the imaging guy was using to take pictures in the room. So, while we were doing this imaging, we also went ahead and looked at the electrical panels, and I guess you can tell which of the electrical panels are feeding the compute units, which of the circuits, and which ones are not, which are feeding the switches and the other low power equipment. But again, this was an interesting way to measure the power usage through the electrical panels. So again, one of the reasons we designed this and set it up the way we was, cost was a big issue. The facility, really, honestly, this is probably the last big system we're going to put in this facility. It's about 20 years old, and this is, we think, probably the last system as we plan for the future. Now, the research office complex data center is a little bit different design. This primarily houses Ranger. We have a couple of other systems, Longhorn, which is our big visualization system, and Corral, which is one of our large storage systems in the room, along with a lot of other support systems. But as I mentioned, we had requested over 12,000 square feet, and it was built in 2007, but 4 years later, we're already out of space. If you notice, we're almost completely occupied in the room. Now, a couple of things we didn't like in the original design for Ranger is each one of these gray boxes is actually a power distribution unit. We needed 1,400 20-amp circuits to run Ranger. And to provide all of that circuit, you have to have tons of panel space. So there's 4 circuit breaker panels in each of these boxes and 21 of these PDUs spread through the room. Ranger occupies this space here. We use in-row cooling on it. All the other systems are actually cooled through the crack units on the side here, but they don't have quite the power density that Ranger has. Ranger is 30 kilowatts per rack, whereas most of the other racks in the room are somewhere between 15 and 20 kilowatts per rack. Again, this is Longhorn down here, and then some of our support systems here. Now, one thing they did do is when we asked them about the design of the data center, they actually built it with future expansion in plans. This wall here is actually, there's nothing on the other side of this wall. It can be a knockdown wall. And we'd actually originally designed that so that we would, hopefully 10 years after we were operating the machine room, we could expand it. Well, it looks like now, 5 years after operating the machine room, we're already going to be expanding it here. Just a picture of Ranger. These are the racks of Ranger here. The end rows have all the storage and login nodes in it. And these are the in-row coolers. Now, these were the older previous in-row coolers that were only 1 foot wide. The Henrys now with the 2 foot wide ones are much better. In fact, these generate an awful lot of noise, and is one of the challenges in the machine room is, you know, we have to wear hearing protection basically if you're going to be in the machine room for any period of time. So we've been exploring flexible and efficient data center designs at TACC. We're kind of looking in the future what we're going to need for the next 5 years or so, and we're trying to plan for about 50 kilowatts per rack and 10 megawatts of total system power in the near future. Now, that's really only 6 megawatts more than what we already have in. This is 10 megawatts in the entire research office complex. We've been trying to encourage the vendors to do more 480 volt power distribution to the racks. We want to really get the efficiency of power to the racks. Now, I mentioned all those PDUs that were spread throughout the room. Now with some new technology, you actually can do in-row PDUs, and we are exploring some of that so that we can get the power as close to the compute racks as possible before having to step it down. We are exploring some exotic cooling ideas. We're not excluding any options here. One of the challenges at the university is our power bill is actually rated by the maximum power draw the campus pulls on any given day in a month. So the university is striving to reduce that maximum load. Well, one of the things we could do is actually put in some thermal storage tanks, use the thermal storage tanks to run all the cooling during the day, and only run the chillers at night to preload the thermal storage tanks. We're also exploring some immersion cooling. We actually have a small project right now that's funded, and that's through the Green Revolution cooling solution here. What they've done is they've laid the rack on the side, filled it up with mineral oil, and you suspend the servers in the mineral oil to provide all your cooling. Again, this is one of our initial research projects. It's probably a little immature. I do know that they've got some deployment and larger scale systems going in. The key aspect of this is it improves the heat transfer and much more efficient than transport of air. Everybody realizes we're really pushing the limits in terms of air cooling on a lot of these systems, and even IBM with the Power 7 system design, you know, they're delivering chill water to each of the processors. So now the downside is this does require some refit of the servers. You have to remove all the fans. You know, you're putting disk drives in oil. That means the disk drives need to be sealed. They don't like spinning at 15,000 RPMs in oil. Disk drives aren't actually sealed. They actually do have little air holes for I guess, pressure variations and so forth. And there is one other thing we have to do on the servers, the thermal paste that's normally used for the processors is actually degrades in mineral oil. It'll dissolve. So they do replace the thermal paste with a thermal paste that doesn't dissolve in the mineral oil. Now, we've been running this setup here for about 1.5 years now. Pretty good success. We've put about 10 kilowatts of power into this rack, and it takes about 300 watts to cool that 10 kilowatts of power. This is completely isolated. Notice it's not in the machine room. It's actually on our loading dock. And all it's being chilled with is there's an evaporative cooler outside that's providing all the cooling for the system. Even in the 100-degree temperatures we've been having all summer, we've been able to run this system like this. Now, they're working on designs where they can go up to about 40 kilowatts a rack and beyond. We hope to deploy a much denser system hopefully soon through some other funding activities. So just to summarize here, we see the data center rack power densities really increasing at a really exponential rate. It's almost keeping up with Moore's law here. And in fact, we're starting to see more and more other data centers struggle with this as virtualization technologies kick in. They're consolidating a lot of servers. So from our point of view, really the efficiency of delivering the power and cooling the heat generated is becoming substantial. You know, we want to drive that PUE down, like Henry said, down to 1.2, even down as close to 1 as possible. Now, air cooling is really reaching the limits. I think I've heard debates here on some air cooling, but I think everybody agrees that when we hit about 80 kilowatts a rack, you just can't move enough air across those to cool it down. But you know, we need to address some of those issues coming up. And you know what? Our future data centers are really going to require some more exotic cooling or customized cooling solutions for these very high power densities. Again, we see this a lot with Power 7 having the chill water delivered right to the nodes. We're going to have to move that cooling as close to the processors and the heat generation as possible. And that's why we're exploring some of these other techniques for cooling. And with that, I'll turn it over to Steve to talk about his clusters.